Microsoft has achieved something truly groundbreaking. They've published a research paper introducing a large language model, LLM, capable of genuine self-improvement. It might sound like something out of science fiction, but this is the real deal, and it's absolutely fascinating. Take a look at this fascinating research paper titled RAR, Math. Small LLMs can master math, reasoning with self-evolved deep thinking. This study is quite remarkable because it shows how a model can enhance its own intelligence through self-directed thinking. The paper introduces R-star math to demonstrate that small language models, SLMs, are capable of rivaling or even surpassing the mathematical reasoning skills of OpenAI's GPT 3.5. What's even more impressive is that these SLMs achieve this without relying on distillation from more advanced models. That concept is just mind-blowing. If you're unfamiliar with model distillation, it's a process where a larger teacher model transfers its knowledge to a smaller student model. Essentially, the teacher model, which is the more advanced version, helps create a streamlined version, the student model, by distilling its knowledge. Here's how it works. The teacher model's knowledge is refined and passed on, enabling the smaller student model to perform tasks similarly to the teacher. For example, think back to when we had 0-1 preview and the actual 0-1. The 0-1 preview was essentially a fine-tuned, smaller-scale version of the original model, designed to mimic its performance, though with slightly reduced capabilities compared to the teacher model. What makes this paper so remarkable is their claim that they can outperform large language models without relying on distillation. It's absolutely mind-blowing. They explain that R math achieves this by leveraging deep reasoning through Monte Carlo tree search. Things get even more fascinating when we dive into the initial benchmarks. On the math benchmark, the improvements are striking. For instance, the Qwen 2.5 Math 7B, a 7 billion parameter large language model, jumps from 58.8% to an impressive 90%. Similarly, the 53 Mini 8B model goes from 41.4% to 86.4%, surpassing the 0-1 preview by 4.5% and even scoring 0.9% higher on the USA Math Olympiad. Now, if you're wondering why this is such a significant achievement, here's why. One of the biggest criticisms of small, large language models, yes, small, large models, is that they've typically been assumed to rely heavily on training data to achieve high scores on benchmarks. Essentially, people thought they were just memorizing the training data. But here's the game changer. This model doesn't rely on being trained on all that data to perform so well. Instead, it has the capability to improve itself to reach these exceptional levels. That's right. This isn't just about data. It's about self-improvement. This is truly fascinating. Here, we have a diagram that provides an overview of the R-star math system, specifically focusing on Monte Carlo tree search, MCTS. Let's break it down. First, this diagram shows how the self-evolution framework works. It's essentially how the model thinks and bootstraps itself to achieve greater intelligence. On the left, we see the Monte Carlo tree search process. This is where the system explores multiple paths, similar to how a person might think through the consequences of their decisions in a decision tree. The small language model acts as a policy generator, creating reasoning steps for potential solutions. Then there's the preference model, which verifies and evaluates each step. I'll explain this in more detail shortly because it's really impressive. Each node in the diagram represents a step in solving the problem. For example, one node might have a value like 0.7 or 0.5. Steps leading to correct solutions are assigned higher values, while incorrect ones get lower values. The system filters these steps, retaining only the high-quality ones, highlighted in green, to construct the final solution. This ensures the AI learns from the best reasoning paths. What's extraordinary here is the self-evolution framework. Monte Carlo tree search is powerful, but to improve a language model, additional processes are necessary. That's where the four-step self-improvement process comes in. Let's go through these steps. Terminal guided Monte Carlo tree. Search, the process begins here. Introducing PPM, Preference Process Model. R2. This step scores results more effectively, using data from previous rounds to refine the model. upgrading the model. For instance, the model starts as R1, round 1, and evolves into R2, then R3. At this stage, the policy leverages the reward model to directly predict Q values during the search, generating higher quality solutions and training data, achieving state-of-the-art performance. In the final round, the system combines the improved reward model with an enhanced policy, culminating in a version of the model that achieves state-of-the-art performance. What's remarkable is how the model starts with limited knowledge and iteratively improves itself to achieve exceptional results. It generates synthetic data and fine-tunes its reasoning with each step, creating a self-reinforcing cycle of improvement. This process is nothing short of incredible. It showcases how AI can evolve and optimize itself through structured frameworks like these. When we analyze the benchmarks, we can see how the model continuously improves its mathematical reasoning capabilities through self-evolved deep thinking. By the second round, the model surpasses GPT-4. Initially, the base model achieves a score of 58.8 in math, but it doesn't perform well on other benchmarks like AMY, where it scores 0. However, after applying the improvement process outlined earlier, the performance increases significantly. For example, it jumps to 75.2, followed by incremental improvements of 10, 50, and 35 points across subsequent rounds. By round 2, the model has already surpassed GPT-4. By round 3, its performance improves even further, and by round 4, it becomes state-of-the-art, even surpassing one. What's remarkable is that this achievement comes from a base model with just 7 billion parameters. Despite its relatively small size, it outperforms state-of-the-art models. While this benchmark specifically focuses on math, it highlights just how advanced these models can become. If a 7 billion parameter base model can outperform GPT-4 or 1, imagine what could be achieved with a mixture of experts or models designed to improve themselves. The potential for future AI development is staggering. Today, I want to discuss how this model enhances itself over time. The process is relatively straightforward. The model first generates solutions, then evaluates them, retrains using the best solutions, and repeats the cycle. This feedback loop is key to continually refining its reasoning capabilities. You might wonder, what happens with unsolved problems? For those, the model employs multiple reasoning attempts, such as additional rollouts or new random seeds, until it finds a solution. This iterative process ensures the model is constantly learning from its failures. What's truly groundbreaking is that after the initial phase, the model generates its own training data. This represents a significant departure from traditional training methods, which often rely on distilling knowledge from larger teacher models. By creating its own training data, the model bypasses the need for manual labeling or large pre-assembled datasets. This approach is not only powerful but also highly efficient and cost-effective, particularly for specialized tasks like mathematical reasoning. Moreover, the model isn't restricted by its original training data. It has the capability to improve and evolve over time, making it a revolutionary step forward in AI development. Remember how, in another paper, perhaps you've seen it on this channel, or maybe not, they discussed the approach to predicting outcomes for models like OpenAI's. They highlighted the difference between outcome-based reward models and process-based reward models. Outcome-based reward models focus solely on whether the final result is correct or not. However, process-based reward models evaluate each step of the process, rewarding partial progress even if the final outcome isn't entirely accurate. For example, imagine solving a math problem step by step. With process-based rewards, each correct step you write down earns a reward, even if your final answer is incorrect. In contrast, with an outcome-based approach, the entire solution is discarded if the final answer is wrong, regardless of the accuracy of individual steps. So, let's say the first 3 steps of your solution are correct, but the last 2 are wrong. With process-based models, you'd still get credit for those 3 correct steps. What I find particularly fascinating about this is how it shifts the focus from just the end result to the quality of the process itself. They actually revise the reward model by implementing a process preference model. They introduced a unique training method that constructs step-by-step positive and negative preference pairs. Let me break this down for you. Essentially, they've changed their approach by using a hybrid method combining process reward modeling and the PPM, process preference model. The PPM trains a model to guide the reasoning process by comparing steps, avoiding the need for precise scores for each step. This makes it more robust and reliable. This is the key innovation in the paper, which is used to drive the Monte Carlo tree search process. To sum it up, the process preference model, PPM, forms the backbone of all-star math, especially in later rounds, where it outperforms traditional process reward model approaches. Initially, they use the process reward model for bootstrapping the system, but once it matures, they transition to a more effective process preference model. This hybrid approach effectively balances the benefits of both methods. Let's take a closer look at the axes. On the x-axis, we can see the number of sampled solutions. As the number of sampled solutions increases, the accuracy also improves, which is expected. This graph clearly shows the correlation between the number of solutions sampled and accuracy. Now, let's focus on the y-axis, which represents accuracy. You'll also notice the different models shown in the graph. For example, the green model, R-star math, is displayed here, along with other models such as Quen2, test of N, and 0-1 mini accuracy, among others. The 0-1 preview model was not tested on the Olympiad or college math benchmarks, but we can still observe the performance of the 0-1 mini across various benchmarks. Interestingly, as we sample more solutions, we see that the R-star math model improves in its responses. Keep in mind that this is a 7 billion parameter model, which is holding its ground against much larger models. And this trend appears to be true for all models, improving accuracy as more solutions are sampled. However, the improvements seem to diminish as we continue sampling, showing less marginal gains with each additional solution. What's really surprising is that, with fewer sampled solutions, R-star math outperforms many of these larger models. This suggests that the model is able to reach higher levels of reasoning with fewer samples, thanks to a more efficient way of processing the information. Upon further analysis, we also see that R-star math is outperforming a 72 billion parameter model, which is quite remarkable. This highlights the effectiveness of this approach and underscores the potential of Monte Carlo's research and the process preference model. The results point to a significant insight. Achieving such high accuracy with fewer sample solutions makes R-star math a highly cost-effective and scalable solution, particularly for tasks that require mathematical reasoning. This might lead us to rethink the potential of smaller models, showing that maybe the claims of superintelligence aren't as far-fetched as we once thought. Another fascinating discovery I found in the paper is that the model generated its own data, as we discussed earlier. What's mind-blowing, though, is that the data it created outperformed GPT-4. As the paper mentions, even when we randomly sampled code-augmented chain-of-thought solutions from our smaller language model, the performance was comparable to or even better than GPT-4's synthesized NummaMath and MetaMath datasets. This suggests that after several rounds of self-evolution, our model's policy-based language models, SLMs, can generate high-quality math solutions. These results highlight the incredible potential of our method, showing that we can self-generate better reasoning data without relying on advanced LLM distillation. This is really remarkable because it means that even the randomly selected reasoning paths generated by the model during training, without necessarily picking the absolute best ones, still outperform the high-quality datasets like NummaMath and MetaMath, which are generated by GPT-4, a much larger and more powerful model. Surpassing these datasets demonstrates the effectiveness of our model's self-evolution process. The quality of these reasoning solutions is not just a lucky outcome. It's the result of the iterative self-evolution process, where after several rounds, the smaller model becomes skilled enough to generate solutions that rival those produced by an advanced model like GPT-4. This is truly incredible because it means we're breaking free from the dependence on large language models. Now, imagine if we had a model that was much larger. If we could use methods like these to improve its performance iteratively, we could potentially create models that are even smarter than future models. While that might sound impossible, think about this. We've taken a 7 billion parameter model and made it generate solutions smarter than GPT-4, which has 1.8 trillion parameters. So, what happens when we apply these methods to even larger models? The possibilities for the future are truly exciting. If you enjoy this video, don't forget to like, share, and subscribe to the channel. See you in the next part.